Hello lovelies, in this video we're going to be going through our OCR Separate Science Chemistry Paper 1. This is the foundation paper that we've written for 2024. So if you're looking for the higher paper or if you're looking for a different example, go back to the playlist or go back to the webpage and make sure you're watching the right video. If you haven't done one of these videos before, what we want you to do is to pause after the question comes up, have a go at it yourself on a bit of paper, you don't need to print anything out, and then play the video. Go through the answers with Charlotte, see where you could have picked up more marks, see what we need to improve on for the real exam.
Here we're told that the melting point of nitrogen is minus 210 degrees C and the boiling point of nitrogen is minus 196 degrees C. Here we're asked to predict the state of nitrogen at minus 125. So let's just visualise this here. So we know that the boiling point of nitrogen is minus 196 degrees C. Now that there is the temperature at which we're going to change from a liquid to a gas. We're also told that the melting point of nitrogen is minus 210. Now that is when we change from a solid and we melt to become a liquid. And we know that temperature is minus 210 degrees C. Well, here in this question, we're asking about the temperature minus 125 degrees C. So really what this question is testing us on is our negative numbers. So we need to know that minus 125 is going to be the highest out of all of these temperatures. And this means that we are a gas. And that's because we're looking at a temperature minus 125, which is warmer than the boiling point of nitrogen, which means it would have been enough energy there for it to boil. So it's a gas. The answer here is A. Methanol has a formula CH3OH, and it is a liquid at room temperature. Here we're asked to identify what type of substance methanol is. So methanol is a molecule. It just exists as one carbon, 4 hydrogens and an oxygen. There is no repeating structure to methanol. It is simply this standalone molecule. And the fact it's a liquid at room temperature means that it has a relatively low boiling point and melting point. We can also see here that it's made up only non-metals. And when we have something made of non-metals, that tells us that it has covalent bonding within its structure. And there's 2 structures that are composed of covalent bonds. That is simple molecules and giant covalent structures. So straight away that does narrow us down here. So if we think about what we actually know about simple molecules and giant covalent structures, we know that simple molecules always have a very low melting and boiling point. Whereas on the other side of things, the giant covalent structures always have a really very high melting and boiling point. Now that alone tells us that because it's a liquid at room temperature, we must have this simple molecule here. So the answer to this is A, simple molecule. In the modern periodic table, elements are arranged in order of their. Now this question is all about recall, isn't it? This is a fact that we're expected to know. So the answer to this is B, atomic number. Remember that periodic table arranges elements in order of their atomic number. If you don't already know that, that's a great fact to learn. Easy marks. During thin layer chromatography, a solvent travels a distance of 7.9 centimetres. And the sample of dye tested travels 5.6 centimetres. Here we're asked to identify the RF value of the dye. Now, to be honest, even without doing any further calculations here, I could identify the answer. I can see the answer is A. And the reason why I know this is because the RF value is always going to be less than 1. So for that reason, A is our answer. But let's look at why, okay? Let's remind you of how we actually calculate the RF value. First things first, let's write down the equation for RF value. Now RF is calculated by taking the distance travelled by the ink or the pigment and dividing it by the distance travelled by the solvent. And really here, the solvent will always travel further than the dye, and that's because it's the solvent that's transporting that dye in the first place. So here, if we put those numbers in, we're going to have 5.6 divided by 7.9. Make sure they're both in terms of the same unit, like here they're both centimetres. And here I get 0.70886, which of course rounds to 0.71, so our answer is A. Now we're asked to identify the formula of aluminium sulfate. Now to do this, we need to know two things. We need to know the charge on the aluminium ion and the charge on the sulfate ion. Well, to find the charge on aluminium, they would really expect you to use your periodic table. So if you go have a look on your periodic table now, you will see that aluminium is in group 3. Now because it's in group 3 and it has 3 electrons in its outer shell, it's going to form Al3+ charged ions. Now, sulfate, on the other hand, is something we just need to know off by heart because we can't find sulfate in the periodic table. Sulfate is SO4 with a charge of 2-. Now, straight away here, looking at the multiple choice options, I can eliminate A because it doesn't have that sulfate ion. That actually says aluminium sulfide if it was balanced. Now here though, I can see I have a 3+ charge on the aluminium, but a 2- charge on the sulfate. So what we want to do here is to balance these charges, and the easiest way to do this is essentially by crossing them over. We have Al2 and then SO4 with a little 3 down here. So see, all I've done there is essentially pull down the numbers of those charges and cross them over to the opposite side here. Now, the reason why this works is because we want to get the same amount of positive charge as we have negative charge. And we have 3+ and 2-. Now, the common charge that they could have would be 6+ and 6-. And we get that by timesing the Al 3+ by 2, which is what we've done here. And we get that by multiplying the SO4 2- by 3. And that's where we get this SO4 with the brackets and the 3 there. Now notice I haven't bothered to write the charges anymore. That's because they balance and cancel out essentially. So we don't need to write them down anymore. So looking at the multiple choice options, I can see that the answer here is going to be D. So D is my answer. So now we're told that there are many different models that can be used to represent a covalently bonded substance. However, they do not all provide the same information. Here we're asked to identify the model that does not show the bonding in a molecule. Dot and cross diagrams do show where bonding is. The overlapping circles and the shared pair of electrons all represent a covalent bond that's been formed. A ball and stick model is a 3D representation involving balls and sticks, essentially like this, but 3D, and each stick does represent a bond, a covalent bond. The 2D representations will look something along these lines, and again, every little stick that we draw here is going to represent a covalent bond. And then finally, we're just left with the chemical formula, so something a bit like CH4. Now see there's no indication of the bonding. We don't know there if the hydrogens are attached to each other or to the carbon, so we don't have information about bonding in the chemical formula. So the answer to this is D. Here we're asked to identify which of the following statement correctly describes a gas. So the first statement is it can be compressed. Well, gases can be compressed. You can make those particles closer together and turn it into a compressed gas. So that one is already correct. If we were short on time, we could just put an A in the box and be done. But as we're here together now, let's take a bit of time just to look through B, C and D and explain why it's not those. So B states that it has a fixed volume but no fixed shape. Well, actually gases don't have a fixed volume. They can fill whatever space they are in, and so that means that their volume can grow essentially. It's not like a liquid where they do indeed have a fixed volume and no fixed shape. You know, the shape fills a container with a liquid, doesn't it? But the volume always stays the same. So B is actually describing a liquid. Next up C, it says it cannot flow. And a lot of people here could get confused because they could associate the word flow with just liquids. But actually both gases and liquids can flow. The only substance that can't flow would be a solid. So C is actually describing a solid. Finally, for D, a fixed volume and a fixed shape. Again, that there's just describing a solid. So here, hopefully you can see that even if A didn't jump out at you straight away as the answer, by identifying the other ones, you can also get your answer in the end as well. So here we've got A as our answer. Now we're asked to identify which of the following is an example of a chemical change. So to answer this, it's worthwhile recapping what a chemical change actually is. And in a chemical change, we have a chemical reaction occurring and new products forming. Whereas with a physical change, the matter may change state or its form, but it's still the same chemical. So here in this case, if we have a look through A, B, C and D, we'll be able to identify where we have a chemical change. Now the evaporation of water is just taking liquid water and changing it to gaseous water. We don't really have any new products, we still have H2O, don't we? So all that we have in A is an example of a physical change, so we can eliminate that. Now for B, we're looking at nitrogen and hydrogen forming ammonia. So to remind ourselves of the equation, that is N2 plus 3H2 goes to 2NH3. Don't have to write that, but I just have. So here I can clearly see that a chemical reaction has taken place and we have a new product. Now that tells us that B is correct. B is an example of a chemical change because we have fit those rules. However, if we look at the others too, just to eliminate those, C is the separation of oxygen from the air. Again, we're just separating things there. There's no chemical reaction occurring at all. And then for D, the melting of ice, that's very similar to the evaporation of water. We have there as a state change from solid H2O to liquid H2O. So we don't have a chemical change happening there either. So we are happy now, 100% sure that B is our answer. Identify which method should be used to separate sand from water. So sand is an insoluble substance. It's tiny little particles, and the water that it's in, it's not dissolved in, okay? So when it comes to separating it, all we need to do is to filter it, and that will separate the two. So the answer to this one is simply going to be A, filtration. So we don't need any processes more complicated than that. Simply a bit of filter paper and a beaker, and away we go. The sand would stay in the filter paper and the water would go through into our beaker. Steel is an alloy of iron and carbon. If 96% of 2 kilograms of steel is iron and the rest is carbon, calculate the mass of carbon. So I think first things first, let's just summarise this information. So we know we have 2 kilograms of steel, and we know that steel is made up of some iron and some carbon, where the iron is 96% and the carbon would be the remainder of that, 4%, which simply comes from the fact that 100 minus 96 gives us 4. So this question wants the mass of carbon, which means we need to find 4% of 2 kilograms. Now we can do that by doing 4 over 100 times by the 2 kilograms, or 0.04 times 2, whatever method you like. So here I get the answer of 0.08 kilograms. And there's nothing there in the options. So let's change this to grams now. We can convert from kilograms to grams by timesing through by 1000. By doing that, I get 80, which I can see is option A, which tells me that my answer to this is A. So there we are, that's the answer. Here we need to identify an experiment that could be carried out to determine if a solid substance is pure. Now this is a method that we just need to go away and learn, okay? So whenever we want to test for a pure substance, we do need to measure its melting point. And the important thing we need to know here is that a pure substance will have a very sharp, definitive melting point. For instance, think of water. The boiling point of water is 100 degrees C. However, an impure substance will have a melting point which is more of a range of values. It's not going to be that sharp, definitive value. So, for that reason here, we've explained it, we've got the answer. All we need to know is that to determine if a solid substance is pure, we need to measure the melting point. So the answer to this one is B. Now we're asked to identify the relative formula mass of calcium nitrate, and they've given us the formula here, which is important because this formula tells us how many of each different type of atom calcium nitrate has. And so to get organised, the first thing I would do is I would make a note of the fact that calcium has a mass number of 40, nitrogen is 14 and oxygen is 16. Now we know that we can work out the MR. So we only have one calcium, we have two nitrogens, which you can see using the brackets that we have two nitrogens. So we do 2 times 14. And then for the oxygens, we actually have 6 because we've got 2 of these O3s. So we're going to add on 6 times 16. Now tidying this up, we have 40 plus 28 plus 96. And if we now just put this into our calculator, we end up finding that the relative formula mass of calcium nitrate is 164. So the answer to this one is C. Here we're asked to identify which is the correct statement about elements in the same group. Now this is a fact that we really need to know. So elements in the same group all have the same number of electrons in their outer shell. So all of the elements in group 1 have 1 electron in their outer shell, all of the elements in group 2 have 2 electrons in their outer shell, and so on. So here we can simply say that D is the correct answer. Elements in the same group have the same number of electrons in their outer shell. A reaction took place where A plus 3B makes 2C. We're told that 2 grams of A reacted with 5 grams of B, and we're asked to work out the mass of C made. Now the rule that we're using here is conservation of mass. So in theory here, if our total reactants, the A and the B, add up to make 2 plus 5, 7 grams, and C is our only product, the mass of C made must be equal to those 7 grams. So the answer to this, the mass of C made, is going to be A, 7 grams. Here we're told that sodium carbonate reacts with sulfuric acid, and we're asked to identify a product formed in this reaction. So first things first, let's remind ourselves of what we make when a carbonate reacts with an acid. And this is just our generic reaction. So a carbonate plus an acid makes a salt plus water plus carbon dioxide. And let's remind ourselves that sulfuric acid forms sulfate salts because that's going to be helpful here to know. So if we have a look at what reactions taken place here, we've got sodium carbonate reacting with sulfuric acid, and using our general reaction there, we can say that we're going to make sodium sulfate and water and carbon dioxide as well. So technically we didn't have to do all of that to answer this. We could have just used our general reaction, but never hurts to put in an extra bit of revision as well. Well, here you can see that carbon dioxide is made in this reaction, and it's made in any reaction where a carbonate and an acid react, and so that here is the answer, C. Calcium reacts with oxygen to form calcium oxide. Calcium is a metal. Here we're asked to complete this sentence using answers from the box. So we know that calcium is a metal because it is found on what side of the periodic table? So the answer to this is the left-hand side. So if I give you a quick reminder of the general shape of our periodic table, what we have is a little staircase separates the metals from the non-metals. So all of our metals are found over here in this really quite large region on the left-hand side of the periodic table, whereas all of our non-metals are found in this much smaller little portion of the periodic table over on the right-hand side. So the answer to this question is that metals are found on the right-hand side of the periodic table. So the electronic structure of calcium is 2882. Now we're asked to identify which group of the periodic table calcium is found, and we're asked just to tick one box. Well, here, of course, we could look up calcium in the periodic table if we needed to. We could find our periodic table, look up calcium, and the groups are going to be the column that it is found in. So here though, even without the periodic table, we have enough information to determine what group calcium is in. The number of electrons in the outer shell of an atom is going to be the same as that group number. So here, because there are 2 electrons in the outer shell, we can see that it is going to be in group 2. So that is a great shortcut way to be able to determine the group if we know the electronic structure. But at the same time, you could just have looked at your periodic table and identified where calcium is, and you will find that it is actually in group 2. Looks somewhere like this on our periodic table. So here we're asked to complete the diagram to show the electronic structure of oxygen. So the first thing that I would do in this case is I would go to my periodic table and look for oxygen. So when I find oxygen, I can see that it looks like this on the periodic table. Now, this bottom number represents the proton number or the atomic number. And it's important that we know that when we have an atom like we do here, the proton number is exactly the same as the number of electrons. So here we can see that there are 8 electrons in an atom of oxygen. So now we can use this fact to draw this electronic structure. So 8 electrons in total. It's important that we know that in the first shell, so the most innermost shell of oxygen, we can only fit 2 electrons. In subsequent shells, we can fit in as many as 8. But here we just need 8 in total. So we've already used 2, so then we've got 3, 4, 5, 6, 7, 8 electrons. So there, what we have here in this drawing is the electronic structure of oxygen. See, we have 2 electrons in its innermost shell and then 6 in its next shell to represent the 8 electrons in total in an oxygen atom. So now we're told that the reaction between calcium and oxygen is given by 2Ca plus O2 makes 2CaO. So what that's saying is that calcium reacts with oxygen to form calcium oxide. Now we're asked to complete these sentences using the words in the box. So here we're asked, what does calcium do with respect to electrons? Does it gain an electron? Does it lose 2 electrons? Or does it gain 2 electrons? Well, if you remember from the previous part of this question, we were told the electronic configuration of calcium is 2882, where this last 2 is the outer shell of the calcium. To get a full outer shell, that calcium could technically do one of 2 things. It could lose those 2 electrons, or it could gain 6. Now, gaining 6 electrons will be far harder work than just losing 2. So what is going to happen is it's going to take the easiest route, and that calcium atom is going to lose 2 electrons. So we can fill in the blank here. Calcium loses 2 electrons. And then we're asked, what does oxygen do? So we can look at our diagram here. So we can see we've got 2 electrons in the innermost shell and then 6 in the next. And this is a different way of writing the electronic configuration of oxygen. Here we can see that we have 6 electrons in its outer shell. So again, to get a full outer shell, oxygen has 2 options. Either it can gain 2 to get up to that full number of electrons of 8 that it can hold in its shell, or it could lose 6. Now it's going to be much easier to simply gain 2 electrons, and that therefore is going to be what happens here. So we are going to, in this case, gain 2 electrons. And that will ensure that we have a full outer shell in both the calcium and the oxygen. Now we're asked to identify the relative charge of a calcium ion. So there's a few different ways we could look at this. Of course, we knew that its electronic configuration was 2882. And we know from earlier, in order to get this full outer shell that every metal and non-metal is striving for all the time, we are going to have to lose 2 electrons. Now, if we think about this, if we're losing something negative, and don't forget, an electron is a negative particle. It has a charge of -1. If we lose something negative, then we become more positive, even if it's just a negative thought or something. You lose something negative, and in turn you become more positive. So here in this case, when we lose 2 electrons, we're going to become more positive. And so what we have is a 2 positive charge for that calcium ion. As I mentioned, there are other ways of learning this. Without much understanding, perhaps, you could just learn that group 1 always will form an ion with just simply a positive 1 charge. All of the substances in group 2 will always form a +2 charge, and all of the substances in group 3 will always form a +3 charge. So that could be a simple, quick hack, a quick cheat code for remembering this, but I really, really recommend that you understand where these charges are coming from. And it's simply a case of, are we gaining a negative thing? If we are, we're a negative ion. And if we're losing a negative thing, we're becoming a bit more positive, so we become a positive ion. So now we're asked, what kind of bonding is found in calcium oxide? And there's a really quick way to identify what kind of bonding a substance has. What you need to do is to look at what atoms make it up and ask yourselves, are those metals or non-metals? Now, from what we said earlier with the periodic table, calcium is found on the left-hand side of the periodic table. And so calcium is a metal. Oxygen, on the other hand, is on the right-hand side of the periodic table. And so for that reason, that is a non-metal. Whenever you have a metal and a non-metal bonding together, they form an ionic bond. If we just had non-metal atoms together, then they form covalent bonds together when they bond together. And metallic would be we simply have a metal on its own. So in this case, the type of bonding found in calcium oxide is simply ionic. So finally, we're asked to complete the dot and cross diagram of calcium oxide. Show outer electrons only. So to do this, we need to remember that electronic configuration of calcium and of oxygen. And the oxygen one, in fairness, we've already drawn the full electronic configuration of it. Here, though, you can see we only want to show the outer electrons. If we start with oxygen, just because we drew that earlier, you remember that it had 6 electrons in its outermost shell. So we can start by drawing 6 electrons in the outer shell of oxygen. Calcium on the other side, you can see that in its outer shell it only has 2 electrons. So initially it would have 2 electrons in its outer shell. But when this bonding takes place, calcium's 2 electrons are going to get donated to the oxygen. Remember, we said that it is giving up its 2 electrons and becoming 2+, becoming more positive. And the oxygen in turn is going to gain 2 electrons and become 2- in charge. So here, if we remove now these little arrows because we don't need them, you are going to be able to see the dot and cross diagram for calcium oxide. See that the calcium gave up its 2 electrons, becoming a 2+ ion, and it gave them to the oxygen, which received them to get a full outer shell of its own and become a 2- ion. Iron is a metal. Iron is used in electricity pylons as it is a good conductor of electricity, and it can be used to make machinery parts as it is malleable. Here in part A, we're asked to explain why iron is malleable. So to help explain this, I'm going to start by just drawing a little diagram. So in iron, all of its atoms are in layers, okay? And the fact that they're in these regular lattice layers means that they can slide over each other very easily. And so our explanation for why iron is malleable is that they have layers that can slide over each other. And that's all we need to say to explain why any metal is malleable. Okay, so now we're asked to explain why iron is a good conductor of electricity. And again, this answer, it's going to work for any metal, not just iron. So again, I'm going to draw a little diagram just to help you visualize this. So iron is made up of these layers of metal ions and a sea of delocalized electrons. Again, that's true of all metals. So the reason why it's a good conductor of electricity is the fact that it has these delocalized electrons that are free to move. And that is why iron, or any metal, is a good conductor of electricity. The salt iron chloride can be made from reacting iron with chlorine. Iron chloride is an ionic compound with ionic bonds. Here we're asked to identify the correct definition of an ionic bond. So we've got strong electrostatic attraction between oppositely charged ions. Well, that is correct. An ionic bond always forms between a positive ion and a negative ion. And because they're oppositely charged, they have this strong electrostatic attraction. If we look through the other options, just to explain why they're not correct, we can't have a strong electrostatic attraction between atoms because they're not charged, so they won't have any attraction between them. Next up, strong electrostatic attraction between metal ions and delocalized electrons. Well, that would be correct if we were talking about a metallic bond, but it is not correct when talking about ionic bonds. And finally, strong electrostatic attraction between electrons. Well, electrons have the same charge, so they wouldn't be attracted, they would actually repel each other. So that one is incorrect too. Next up, we're asked to draw a two-dimensional model of an ionic lattice. And it doesn't specify which ionic lattice, so I would just choose some positive and some negative ions in an alternating arrangement. So we've got positive ions next to negative ions with a repeating alternating pattern. And you can make this as big as you like, just make sure that you have at least two of each, the positive and the negative, arranged in that alternating arrangement. So here we're told that iron chloride, as we talked about earlier, conducts electricity when in solution but not when solid. And here we're asked to explain why. So now for the next part of this question. We're told that steel is an alloy made from iron and carbon. Steel is a harder material than iron. We're told that an alloy is an example of a formulation, and we're asked to describe what is meant by the term formulation. Now, if you don't know this definition already, make a note of it with me. Okay, so a formulation is a mixture designed to produce a useful product. And the key part of this definition is the fact that it's a useful product. So there's many examples of that. We'll see one in a moment. But yeah, so that's the definition of a formulation. If you don't know that, then make a flashcard or some notes on it now and get memorizing it. Okay, so now we're asked to identify which of the following is an example of a formulation. So the answer to this one is going to be paracetamol. And the reason for that is that paracetamol is obviously useful. The reason why they have made it is because it's going to help relieve pain. That is its use, and it is very clear. Lots of these other products, perhaps they could be useful, but it hasn't been designed specifically to be made for that reason. So for the last part of this question, we're told that steel is more brittle than iron, and we're asked to explain why it's more brittle. So to answer this, I'm going to draw a little diagram just to aid the explanation. So iron is made of these repeating iron atoms arranged in layers in this regular lattice structure. Steel, on the other hand, is made up of both iron and carbon atoms. And because those carbon atoms are a different size to the iron atoms, it disrupts those layers, which stops them from being able to slide over each other as easily. So looking at this diagram, let's give it a little label so we can see we have our iron atoms and our carbon atoms in this alloy of steel. So going back to the question now, explain why steel is more brittle than iron for 2 marks. First thing we want to state is that steel is made of different sized atoms. For the second mark, we're going to state that the layers cannot slide over each other as easily in steel than in iron. And that is what's going to give us our answer as to why steel is more brittle than iron. I hope that makes sense, and I hope the little diagrams just aided you in visualising that a bit better. Here we're told that the solution of copper 2 sulfate was electrolysed using 2 copper electrodes. This process was carried out at different currents, so we did it at 0.1 amps, 0.2 amps, 0.3 amps and 0.4 amps. The mass of the anode and the cathode were measured using a balance before and after the electrolysis. Results were recorded in the table below. So here we're asked to describe the results in the table. And you can see it's a 3-mark question. So we need 3 good points in our description. So starting off, let's have a look at the mass of the anode before and after electrolysis. So if I look at it, I can see that it started at 20 grams to begin with, but in every different current there, you can see that the mass has gone down. So the first thing that we can say is that the mass of the anode decreases after electrolysis, and that gets us our first mark. So the next thing to think about, let's do similar, but this time for the cathode. You can see that all of the cathodes start with a mass of 20 grams, but then after electrolysis, this time, you can see that they all go up. So they all gain mass. So the second mark we can get here is that the mass of the cathode increases after electrolysis. So now we need to have a look at the bigger picture of this experiment. And we haven't really talked about how current affects things yet. But you can see that as that mass of the anode is going to decrease, you can see that as the current gets bigger, that decrease gets bigger. And the same with the cathode. The mass of that increases, but that increase gets bigger as the current increases. So the final thing we can say is that the change in mass increases as the current increases. And just to make sure that you can really clearly see that, of course, when we have 0.1 amps, it goes from 20 to 20.05, so it has increased by 0.05. Whereas when it's 0.2 amps, I can see it increases by 0.08. 3 amps, I can see it increases by 0.18. And finally, at 0.4 amps, I can see that it's increased by 0.31. So I can certainly say that the change in the mass increases as the current increases. So now we're asked to explain the results in the table. Because this is an explain question, we need to give the chemistry behind why this happened. So first, let's have a think about that cathode, where we know that the cathode ended up increasing in mass. So the copper ions end up getting reduced at the cathode. And when they get reduced, they gain electrons and form copper atoms. And by forming copper atoms, that is what's going to cause that increase in mass, because we have made atoms. So let's have a think. We don't have to include this in the answer, but it's helpful for us to visualise it. Let's remind ourselves of the half equation that goes with this. So the copper ions, which are going to be Cu2+, get reduced, which means that they are going to gain electrons and end up forming copper atoms. Now that sort of sums up what we've said, but in an equation. So I think just to help you understand it and to link it with those half equations, it's helpful to write it down. So now we have the other side over at the anode. So at the anode, the copper atoms end up being oxidized, so they lose electrons, forming copper ions, and therefore going into the solution. Now that leads to this decrease in mass, because whereas we had atoms, we don't have them after this oxidation. So let's look at the half equation, just to link this with the half equation side, of course. So we've got copper goes to copper 2 plus ions plus 2 electrons. And that is the reason why we get a decrease in mass at the anode. So quite a challenging question, that I think, but hopefully that's clear. Now we're asked to calculate the percentage increase in mass of the cathode when we use a 0.4 amp current. So let's remind ourselves of these results from the previous question. We're just looking here at the 0.4 amp current and the cathode's increase in mass. So let's remind ourselves now of that equation for percentage increase, because of course we need that, don't we? Percentage increase is going to be equal to the increase or the difference between the values divided by the original value where we started from, and then we times it by 100 to make that percentage. So in this case, we want 20.31 minus 20.00 divided by that original mass of 20.00, and then we times it by 100. Putting this into our calculator, I end up finding it to be 1.55%. And there's our answer. So next up, we're told that beneath the copper anode, a sludge builds up. Just looks like a little mucky substance underneath that anode. Here we're asked to suggest an explanation for the presence of this sludge. And it's a suggest question, so we don't necessarily know this. We haven't necessarily learnt this in class, but we need to have a good stab at it. And here the suggestion is that maybe that copper anode wasn't pure. Maybe it actually had some impurities within it. So when that electrolysis takes place, the copper ions and the copper atoms are taking part in the process. Any impurities just end up dropping down underneath that anode and creating this sludge. So in this question, we're told that diamond and graphite are allotropes of carbon. And what an allotrope is something which is made of the same atom, but it's just arranged in a different structure to form something slightly different. So we've got diamond and graphite, both made up exclusively of carbon. So we're given a table with their properties. We're told that diamond doesn't conduct electricity. It has a very high melting point of 4,000 degrees C, and it is very hard. Whereas graphite is a good conductor of electricity. It's got a lower melting point of 3,600, and it is soft. So some very different properties there. Now these 6 markers are a little bit different to a normal question. Because with a normal question you would think, oh, it's a 2 marker or a 3 marker. You need to give that many marking points. You need to say that many significant things to get those marks. And here, although this is a 6 marker, certainly giving 6 points would be good. That isn't necessarily what's going to get you the marks. Because if you gave 6 marks about diamond, you probably wouldn't actually get many marks. Because what these 6 markers are looking for is they want you to give a high level of detail and talk about all relevant points. You want to give a full answer discussing a bit of everything, nicely balanced. But you're not necessarily going to get it for just six facts that you lay out that's relevant. It has to answer the question fully to a high level of detail. So let's have a look at how I would suggest answering this question. So here I'm going to start talking about diamond, and I'm going to discuss the structure and properties that diamond has that makes it distinctive and special, and then we'll link it to its properties. So in diamond, every one of its carbon atoms forms 4 strong covalent bonds to other carbon atoms. Now that is very, very distinctive of the carbon atoms in diamond. So now we've talked about the bonding, let's mention the type of structure that diamond has. So diamond has a giant covalent structure. So let's link all this now to the properties. So we've said, haven't we, that diamond has a very high melting point of 4000 degrees C, and it is also very hard. So we need to describe why it has those properties and how it links to what we've said about the bonding and structure. So the reason why it has that very high melting point and it's very hard is because of those strong covalent bonds. It is going to take a lot of energy to overcome those bonds and to break those bonds. That is going to have a direct impact on this high melting point and it being very hard. So the next thing that we want to talk about here is why is it that it doesn't conduct electricity? Well, if we look at each carbon atom would normally have 4 electrons that it could donate to form bonds, and every single one of those does form bonds because it has 4 strong covalent bonds. As a result, there's no spare electrons, there's no delocalized electrons that would be what's needed to conduct electricity. So that's why diamond doesn't conduct. Let's get on to graphite. So in graphite, each carbon atom only forms 3 of these strong covalent bonds. So it doesn't form the 4 that diamond did. And that's one of the main differences between diamond and graphite. So if you're not 100% familiar with those differences, then I would definitely recommend that you make yourself a little flashcard with a nice table comparing the two. So graphite, we've mentioned that each carbon forms only 3 strong covalent bonds. Now we can link it to the properties of graphite. So we can see in the table that there's a lower melting point for graphite and it's also soft. And the reason for that is that graphite forms layers. And those layers, they don't have these strong covalent bonds between them. They've only got weak intermolecular forces. And as a result of these weak intermolecular forces, it's going to be really quite easy to overcome these forces. And so for that reason, we don't have as many strong bonds to break. We've got some that are actually quite weak. And then we have that knock-on effect there of that lowering the melting point and making it softer. So then the final thing really to mention about the properties of graphite is going to be about the fact that it is a good conductor of electricity. So if we think back to the fact it only forms 3 strong covalent bonds, and carbon, of course, it has 4 electrons in its outer shell. So if only 3 of those has gone to form covalent bonds, then we're going to have 1 left. And that one that's left is delocalized, which means that it is going to be free to move through the layers that are formed in graphite, and it can carry that charge. And that there is what's required for something to conduct electricity. So that is why graphite is a conductor of electricity, because it has delocalized electron which is free to move through the layers. So let's just look at some of the key facts that's important to know about diamond and graphite, the key words that are going to bring you in the marks in an exam. So for diamond, knowing that you have 4 strong covalent bonds, that you have a giant structure, and then for graphite, that we only have 3 strong covalent bonds and that we have layers formed. Also, the fact that graphite has 1 delocalized electron for every carbon, and in diamond you actually have no delocalized electrons. If we were to strip back everything here that we have said, those are the key facts that you can link to anything if you learn those. So I'd really recommend that you learn those key facts. Draw up a nice little table in your notes to compare diamond and graphite and get learning it. And it will really impact you because these questions always come up in the exam. So here we're given a picture of another allotrope of carbon called Buckminster fullerene. Here we're asked to identify the formula of Buckminster fullerene. Now here you see it's just an identify question. This is really just testing your recall. This is just a fact that they have expected you to memorise. So the answer to this is C60. So if you don't know that already, add it to a flashcard and get memorising it. Buckminster fullerene has a low melting point and is slippery. Explain why. We're asked here to use the words in the box to help us out, so we know we need to mention intermolecular forces and energy. So the reason for Buckminster fullerene's low melting point and its slipperiness is that there are weak intermolecular forces between these Buckminster fullerene molecules. So whenever we have weak intermolecular forces, that means that we are only going to need a little bit of energy to overcome those forces. And therefore, it's not going to take much energy to melt it. And also, they can slide against each other because just a small force that might be applied to these molecules would cause them to slip past each other because they only have these weak intermolecular forces. So there is going to be a perfect answer for us. So weak intermolecular forces and only a little bit of energy is needed to overcome those forces. Perfect. So Buckminster fullerene was one of the first nanoparticles discovered. It's used to deliver drugs in the body, acts as a catalyst and as a lubricant. We're asked here to state the size of the nanoparticles. And again, because it just says state the size of the nanoparticles, if we have a look at these options, this again is just a recall question. They don't expect us to use our knowledge or come up with an answer from our knowledge. No, they just expect us just to know this answer. And a nanoparticle is a particle with a size in the range of 1 nanometer to 100 nanometers. So we would simply tick the box here and just know this is a fact that they expect you to have memorised. So get to work on that if you don't already know it. So here we're asked to state the property of a nanoparticle which makes it good to use as a catalyst. So here we need to know that that property of a nanoparticle, which is why we use it as a catalyst, is that it has a very large surface area to volume ratio. So this is a little fact that we're expected to know. So if you don't know this one, perfect for a flashcard. So some people have expressed concerns about the widespread use of nanoparticles. Here we're asked to give 2 possible risks of this use of nanoparticles. So the first thing that we can say here is that these nanoparticles may be able to catalyse harmful reactions in the body. And so that, of course, is a risk of using them. Another risk that we could say in this case is that toxic substances may be able to bind to them and therefore find a way to enter the body. So this would be another risk associated with nanoparticles. So at the minute we have 2 risks. Of course, these might not be the 2 that you think of first. There might be another one you think of instead. So it's always good to have a third option in these 2 possible risk ones, and then you can always pick and mix which one you use. So the third option is that they could enter and accumulate inside our lungs and therefore cause damage to our lungs. So here we have 3 different options that are possible risks of the use of nanoparticles. Here you can use any 2 of those, just pick the 2 that you prefer and get learning them. The reaction of sodium carbonate with ethanoic acid is an example of an endothermic reaction. A method used to investigate the temperature change when 10 grams of sodium carbonate is added to 50 centimetres cubed of ethanoic acid is 1. Place a polystyrene cup inside a glass beaker. 2. Measure 50 centimetres cubed of ethanoic acid and place in the cup. 3. Measure 10 grams of sodium carbonate. 4. Put a thermometer in the cup. 5. Record the temperature of the ethanoic acid. 6. Add the sodium carbonate to the cup. 7. Stir. And 8. Record the highest and lowest temperature reached by the solution. So here in our first part of this question, we're asked to give 2 ways that the method could be changed to improve the accuracy of the results. So in a question like this, we need to look at our method and think, what are we lacking here? So let's look at a few of the things we could do to improve this. One thing is, maybe we can put a lid on our cup. Because the problem is here is when we use that thermometer, some of the heat might be leaking to the surroundings. For 2, we can simply do this whole thing again and repeat it and take a mean. So that's going to eliminate any little anomalies that might pop up, things that we do wrong. Alternatively, some other things you could have said instead. Maybe you could use a more accurate thermometer, perhaps a digital thermometer if we've used an analog one. Or alternatively, on a very similar theme to that, we could use a more accurate balance. Of course, you can see that we're measuring 10 grams of sodium carbonate. What about if instead we had 10.0 or 10.00? Now that would be an example of a more accurate measurement where we've got it to more decimal places. So using a more accurate balance would also be a great way that we can improve the accuracy of our results. So next up, we're asked to suggest why a polystyrene cup was used. So we need to think, why did they choose that material over something else? Why did they not just use a glass beaker or something similar to that? So the reason why we do use this polystyrene cup is because polystyrene is a heat insulating material. So by using this and by doing our reaction in a polystyrene cup rather than an alternative material, we're going to reduce heat loss to the surroundings and therefore make it more likely that that temperature change that we are measuring isn't going to be inaccurate. So now we're asked to explain what is meant by an endothermic reaction. So an endothermic reaction is a reaction which is going to take in energy from the surroundings. So we need to remember that important fact that the energy is taken in from the surroundings. So as this is such an important thing to remember, let me tell you an easy-ish way to remember this little fact. So endothermic, let's think about the word for a moment. So the endo bit is a bit like the word in or into. And thermic refers to heat. So that means that the word endothermic is talking about taking heat in. So then if we look at the word exothermic now, and again we sort of pull that word away and think about what it means. We've got the part of exo, and exo sounds a lot like the word exit, which is like the way out, isn't it? And thermic again is still going to refer to heat energy, just like a thermometer or thermals or something like that. So exothermic refers to giving heat out. And that there is the difference between endothermic and exothermic. So here we're asked to complete the enthalpy profile diagram for an endothermic reaction like that observed between sodium carbonate and ethanoic acid. And we're asked to label the activation energy. So here in this case, we need to know that we start with our reactants. And because it's endothermic, so it's taking energy in, that means that our products are going to end up with more energy than our reactants had. So that means that our products are going to be a horizontal line higher up than the line of the reactants. So then we draw ourselves a nice little hump, starting at the line for the reactants, going above the products, and then ending at the line of the products. So here we're asked to label the activation energy, and the activation energy will be the line starting at the reactants, going all the way up to that peak of our hump that we've drawn on. So this green line, this green arrow, represents the activation energy. And here we've correctly labelled on the reactants the products being at a higher point than the reactants and included the activation energy. And that is going to be how we get our 2 marks in this question. The air in the atmosphere is an example of a mixture of substances, including oxygen, nitrogen, carbon dioxide, and trace amounts of argon. In part A, we're asked to identify the mixture from the following samples. So here it's testing our understanding of what a mixture is. And in a mixture, we have different substances that are not chemically bonded to each other. So if I look at A here, I can see I've got these dark circles. And then also in this container, I've got these diatomic molecules here. Now, the dark circles and these diatomic molecules are not joined together. And that makes this a mixture. So the answer here is A. If we look at B and C though, just to clarify this, you can see in B we have dark circles and white circles. However, they are chemically bonded. You see they're all together, combined, and everything within this container is the same. It's those same combination of 2 dark, 1 white circles. And then in C, everything is the same again. It's just all these diatomic white molecules. So for that reason, A is the only mixture that we have here. So for B, the different substances in the air can be separated. Here we're asked to identify the process that can be used to separate the substances in the air from each other. And the thing to remember here is we've got several different substances within the air. And each of these different substances, say the oxygen and the nitrogen and the carbon dioxide, they will all have different boiling points. And we can use that fact here to separate these. We're going to use fractional distillation here because we have several different substances in this mixture. It's not just 2 that we need to separate from each other, it's many. And that's why we use the fractional distillation, because we've got several different components for this mixture. So now we are asked to state the property of the substances in air which enable them to be separated using this method. And we mentioned it just then. It's the fact that they have different boiling points that enables us to separate them using fractional distillation. So that there is our answer. So for C, we've got the mass spectrum of a sample of argon is shown below here. The mass spectrum shows the percentage abundance of the isotopes of the element argon. Now we're asked to complete the sentence about isotopes, and we're asked to pick the words in the box. Isotopes are atoms of the same element with a different number of something and the same number of something else. Now this is such an important definition. It comes up absolutely all the time. And we need to know that isotopes have a different number of neutrons and the same number of protons. So in the periodic table, argon is represented in the following way. So let's write this a bit bigger. So we've got argon and there's 40 on the top and 18 on the bottom. Now let's remind ourselves of what each of those numbers actually mean. So the 40 there is the mass number. And the mass number is also the same as the sum of the number of protons and the number of neutrons. So it is the number of protons plus the number of neutrons. Now on the bottom here, we have got 18. Now this here is our atomic or proton number. And certainly if we know it as the proton number, it's quite clear that this atomic number gives us the number of protons. So already we've got information that we can complete this. So here we're asked to write down the number of protons, neutrons and electrons in an atom of argon-40. So the number of protons, we know it's 18. It's the same as that atomic number. Now for the number of neutrons, we need to use the fact that 40 is equal to the number of protons plus neutrons. And of course, we know that we have 18 protons. So that means that 40 is equal to 18 protons plus the neutrons. So that means that if we subtract the 18 protons from the 40, we get the number of neutrons. And in this case, that gives us 22. Now, finally, we need the number of electrons, okay? So here we have an atom of argon-40. And it's really important that we know that in an atom, there's no overall charge. So in an atom, that means that those charged particles are balanced. We have the same number of positive particles as we do negative particles. And that's what gives it that neutral charge. So we need to use the fact that in an atom, the number of protons is equal to the number of electrons. And therefore, the number of electrons in this case is also going to be 18. It is just the same as the number of protons. Here we're told that sulfuric acid is an example of a strong acid. Here we're asked to identify the ion present in sulfuric acid that makes it an acid. And here you see it's just an identify question. So this isn't like a big explain or anything, we just need to know this fact and have it memorised. So it doesn't matter that we're talking about sulfuric acid here. Any acid under the sun, the ion present that is going to ensure that it is an acid and acts as an acid is going to be the H+ ion. So for B, when an alkali is added to the acid, a neutralisation reaction takes place. Here we're asked to identify the pH of the solution formed in a neutralisation reaction. So here it's very important, again this is just another fact that we need to know, that when neutralisation takes place, or if we just have any neutral solution, that solution will have a pH equal to 7. Here we're told that universal indicator is used to measure the approximate pH of a solution. Here we're asked to give the colour of the universal indicator when the solution is neutralised. So this here sort of follows on from what we just said. We would have had to have correctly identified that neutral solutions have a pH of 7. And here we need to know that when we have a pH of 7, universal indicator will turn green. Here we're told that we have 4 test tubes, each with a different metal, and we've added 20 centimetre cubed of dilute sulfuric acid to them. We made some observations, and here is a little table summarising them. So we can see that with sodium, we had a violent reaction. With gold, we had no reaction. With zinc, we had bubbles of gas formed and the metal dissolved. And in calcium, you can see that the bubbles of gas rapidly were released and heat was given off. So here we're asked to write the names of the 4 metals in order of their reactivity using that information that we just saw. So here we need to look at these and think, well, which of these observations would correspond to the most reactive of them? And I think looking at these, it's clear that the most reactive is going to be the one that had that violent reaction. So that here is going to be sodium. We'll cross that one out. So on the flip side, let's think, well, which is the least reactive then? And out of these, the least reactive is going to be the one that didn't actually have any reaction at all, and that is gold. So now we're left with just zinc and calcium, and we need to compare them and determine which of those would be the most reactive. So with zinc, we're told that bubbles of gas were formed, and calcium, we were also told that bubbles of gas were formed. But for calcium, the bubbles of gas were rapidly released. And that increase in the speed tells us that the calcium is what is more reactive. So I'm going to write down calcium as my second most reactive out of these metals. And my third most reactive would be the zinc. So now we're asked to complete the word equation for the reaction between zinc and sulfuric acid. So here it's important that we remember our facts. So whenever we have a metal and it reacts with an acid, we need to know that we will always form a metal salt and hydrogen. So, using that fact here, if we go back and look at this equation, we're going to form zinc sulfate and hydrogen. And the reason why it's zinc sulfate is because sulfuric acid always forms sulfate salts. So that is our answer. And if you weren't aware of it, make sure that you know that this is the standard reaction of a metal with an acid. Paper chromatography can be used to identify the presence of different dyes. The chromatogram below shows the results of an experiment to investigate the composition of different inks. Spots of ink are placed on a pencil line using a pipette. Here we're asked to identify the stationary phase used. Now this is another one of those little facts that we're expected to know. So paper chromatography uses the stationary phase of simply paper. And by stationary phase, literally we mean what is the component of this chromatography which remains stationary. Now that is the paper, because the paper just stays there while the mobile phase moves through the paper. Okay? That brings us on to the next part where we're asked to identify the mobile phase used. Now the mobile phase is a solvent. Of course, you could give an example of a solvent here, or you could simply say water. All of those would still give us our mark. But what happens here is the solvent is mobile in the chromatography. You will place the stationary phase in the solvent, and the solvent will almost get soaked up through the stationary phase of that paper and move, taking the dissolved dyes in it. And that is how we get all of these different spots arising on the paper. Next up, we're asked to suggest why a pencil line is used rather than a pen line. Well, the explanation here comes from the fact that if we drew on a pen line, then that pen line would also dissolve in the solvent. And as a result, it's going to run and ruin our results. Whereas a pencil line will not dissolve, and we won't get this problem. So that's why we use a pencil line. The table below shows the RF values for some different dyes. So we've got blue, red, yellow. And in this question, part D, we're asked to identify the dye in sample X and to show how we find our answer. So first things first, let's remind ourselves of the formula for the RF value. So the RF value is calculated by taking the distance moved by the dye or whatever substance we're looking at and dividing it by the distance moved by the solvent. So that means we need to get our rulers out, okay? And we need to measure the distance from the pencil line to that dot in the X column, okay? So we're going to get our rulers out and measure that distance. And we're also going to measure the distance from the pencil line again up to the solvent front. Now, don't worry if you think, oh, if I'm measuring this on a screen right now or on paper or I've half-sized it on the printing, because this is a ratio, it doesn't actually matter your measurements exactly. Your RF value will still come out as 0.2 or thereabouts, okay? So just take each measurement and you'll notice you will get 0.2 or at least very close. Now that means that you're going to say that blue is the dye here. And that's your answer. So next we're asked to explain how chromatography can be used to determine if a substance is pure or impure. Now here we will say that pure substances will only produce one spot on the chromatogram. However, an impure substance will show two or more different spots on the chromatogram. And that's how we can distinguish between a pure or an impure substance. So just to recap, to get those 2 marks, chromatography can be used to determine if a substance is pure by seeing only one spot and impure if there are 2 or more spots on the chromatogram. Good work. A different type of chromatography, called gas chromatography, can be used to test blood samples for the presence of drugs. Here we're asked to describe how different chemicals present in a blood sample are separated using gas chromatography. So what happens is gas chromatography is your sample gets vaporized so that it becomes a gas. But then different chemicals within that gaseous sample are going to travel at different speeds. They're not all going to travel at the exact same speed. They're going to travel different speeds. And then as a result, when it comes to the detector at the end of this, they're going to leave our gas chromatography machine at different times and get detected at different times. Now, this amount of time it takes in the machine is called the retention time, and that is what we use in gas chromatography instead of RF values in the paper chromatography. So here, just to summarize and recap, the way in which different chemicals in a sample will be separated using gas chromatography is using the fact that different chemicals will travel at different speeds and therefore they will leave the machine at different times. And that there will give us our 2 marks. During this process, a gas chromatogram is produced. And here we've got a diagram of one here. We can see we've got abundance on the y-axis and retention time on the x-axis. Here we're asked to describe what can be deduced from the gas chromatogram above. So here I can see we have got A, B and C. The fact that we've got 3 distinct different peaks tells us that 3 substances are present in this sample. And that's the first thing that we can say. Another thing that we can say is that out of these, C is the most abundant. If you look at its peak, you can see its peak is much larger than the others. Now finally, A and B, you can see they both peak at the same point. And for that reason, we can say that equal amounts of A and B are present in this sample. And that would be our analysis of this. Now this question, you can see it's only a 2-mark question. So we only actually have to say 2 of those points to get the full marks. So if you can understand all 3, brilliant, you can definitely get full marks in this question.
Well done for making it to the end of this video. If you made it this far, I'm really, really proud of your hard work and you deserve to have a great exam.